Welcome back to another electrifying episode of our Note Boost Engineering Exploration series. Today, we're delving into the core principles of electrical circuits, unravelling Ohm's law, dissecting the role of resistors, and uncovering the nuances of circuit configurations. I'm Sean, and with me is Jordan. Let's start our journey with the bedrock of electrical engineering, Ohm's law. The golden rule governs the relationship between voltage, current, and resistance in a circuit. Ohm's law was formulated by German physicist Georg Simon Ohm in the 19th century. It provides a fundamental understanding of how these three key parameters interact to determine the behavior of electrical circuits.
Absolutely, Sean. Imagine a simple circuit comprising a 12-volt battery and two resistors connected in series. One resistor has a resistance of 4 ohms, while the other has a resistance of 6 ohms. Applying Ohm's law allows us to calculate the circuit and determine various parameters, such as the total resistance and current flowing through it.
Let's apply Ohm's law to this circuit. We have a 12-volt battery and two resistors in series. The first resistor has a resistance of 4 ohms, and the second resistor has a resistance of 6 ohms.
Right, so to find the total resistance of the circuit, we simply add the individual resistances together since they're in series. That gives us 4 ohms plus 6 ohms, which equals 10 ohms.
Now that we have the total resistance, we can use Ohm's law to find the current flowing through the circuit. Ohm's law states that current I equals voltage V divided by resistance R. So, with a voltage of 12 volts and a total resistance of 10 ohms, the current will be 12 volts divided by 10 ohms, which equals 1.2 amps.
That's correct, Sean. Now, with the current flowing through the circuit determined, we can also calculate the voltage drop across each resistor using Ohm's law. Since the resistors are in series, the current through both resistors will be the same. The voltage drop across the 4 ohm resistor will be the current 1.2 amps multiplied by the resistance for ohms, which equals 4.8 volts. The voltage drop across the 6 ohm resistor will also be 7.2 volts.
So, to recap, in this circuit, we found that the total resistance is 10 ohms, the current flowing through it is 1.2 amps, and the voltage drop across each resistor is 4.8 volts and 7.2 volts, together adding up to the 12-volt supply.
Exploring series and parallel circuits. Let's embark on a deeper exploration of electrical circuits by examining two fundamental configurations, series and parallel circuits. In a series circuit, components are meticulously linked end to end, forging a singular pathway for the current to navigate.
Indeed, Jordan, picture this. Electrons traversing through a series circuit encounter each component sequentially, akin to cars navigating a single-lane road. What's remarkable is that the current remains uniform throughout the circuit, flowing with consistency through each resistor or any other component in the chain.
Precisely, Sean. Now, let's contrast this with parallel circuits. Here, the arrangement is markedly different. Components are interconnected across each other, resembling a network of intersecting roads rather than a linear path. This design allows for the creation of multiple branches, offering distinct pathways for the current to travel.
Indeed, in a parallel circuit, each branch operates independently, akin to vehicles traversing different roads in a bustling city. What's fascinating is that a malfunction or disruption in one branch does not impede the operation of the others, offering built-in redundancy and enhancing the circuit's robustness.
Absolutely, Sean. This inherent redundancy is particularly advantageous in critical systems where uninterrupted operation is paramount. By providing multiple pathways for current flow, parallel circuits ensure that a failure in one component or branch does not lead to a complete system shutdown, thereby enhancing reliability and fault tolerance.
Whether it's the precision of a series circuit or the resilience of a parallel arrangement, understanding these configurations is crucial for designing and troubleshooting electrical circuits in various applications.
Resistors are accompanied by specific ratings indicating their maximum power dissipation, tolerance, and temperature coefficient. These ratings serve as vital guidelines to ensure that resistors operate within their designated parameters safeguarding against overheating or premature failure.
Whether it's the precision of a series circuit or the resilience of a parallel arrangement, understanding these configurations is crucial for designing and troubleshooting electrical circuits in various applications.
For example, a resistor with color bands of brown, black, and red signifies a resistance value of 1, 0, and then 2 zeros, translating to 1 kiloohms. Additionally, the fourth band, often gold or silver, indicates the tolerance level of the resistor. A gold band signifies a tolerance of plus 5%, while a silver band represents plus 10%.
Tolerance is a crucial aspect to consider when selecting resistors for precision applications. A lower tolerance indicates greater accuracy in maintaining the specified resistance value. For critical circuits requiring precise control, resistors with tighter tolerances are preferred to ensure consistent performance.
Moreover, it's imperative to consider the power rating of resistors, denoted in watts. This rating indicates the maximum amount of power the resistor can dissipate without overheating or sustaining damage. For applications involving high currents or power dissipation, selecting resistors with higher power ratings is essential to prevent failure.
By meticulously considering these ratings and characteristics, engineers can ensure that resistors are appropriately selected for their intended application, thereby optimizing circuit performance and reliability. Now, let's delve into the versatile capabilities of multimeters and explore essential measurement techniques used in electronic diagnostics and analysis. Multimeters serve as indispensable tools for accurately measuring various electrical parameters, including resistance, voltage, and current.
Absolutely, Sean. Let's start with resistance measurement, a fundamental aspect of circuit analysis. By setting the multimeter to the resistance measurement mode and selecting the appropriate range, users can precisely determine the resistance of circuit components.
Indeed, Jordan, but remember you can only measure resistance on a dead circuit. Then to measure resistance, simply connect the probes of the multimeter to the terminals of the resistor under test. Ensure a secure connection and avoid touching the probes with your fingers to prevent erroneous readings. The multimeter will display the resistance value in ohms, allowing users to verify component values and troubleshoot circuit issues.
Multimeters also excel in measuring voltage, providing valuable insights into the electrical potential difference across circuit components. To measure voltage, select the appropriate voltage range on the multimeter and connect the probes across the points of interest.
Whether it's the voltage across a power supply, the potential difference across a resistor, or the voltage drop across a diode, multimeters offer accurate voltage measurements essential for circuit analysis and troubleshooting.
Furthermore, multimeters play a crucial role in measuring current, enabling users to assess the flow of electrical charge through circuit elements. To measure current, users must select the appropriate current range on the multimeter and connect it in series with the circuit under test.
Indeed, Jordan, by inserting the multimeter into the circuit path, the current flowing through the circuit passes through the multimeter, allowing for precise current measurement. Multimeters provide valuable insights into circuit behavior, allowing users to verify current levels, diagnose faults, and ensure proper circuit functionality.
As we wrap up our exploration into the intricacies of electrical circuits and measurement techniques, we hope you've gained valuable insights that will empower you in your engineering endeavors.
And be sure to hit the notification bell so you never miss an upload. Until next time, keep innovating, keep exploring, and keep boosting your engineering knowledge. This is Sean, signing off.
And this is Jordan, wishing you happy engineering adventures ahead. Take care.